So, starting out kind of simple. Working on things that we can do. What are some perfect squares that we know? What, as this says, list as many perfect squares as you can. What perfect squares do we put down? 1 is a perfect square. 4. I was going to say, yep. What this is 1 squared that gave me 1. This was 2 squared that gave me 4. This was 3 squared that gave me 9. 4 squared gives me 16. What more can you come up with? 25. I'll do the 5, but then I'm gonna not keep doing the which one we squared to get there. What else we got? 16. Yeah, I got 16. Yeah. 36. 49. 100. We could keep going. They don't ever stop. We don't usually need to go much further than 10 squared. Knowing that 11 is 121 and that 12 is 144 is probably the two slightly higher ones that might be helpful. But usually any higher than that, we expect you to have a calculator for it. Month over. All right, so very similar vein between the first set of options and the next set of options. So we listed perfect squares when we were squaring numbers. How are we going to get perfect cubes? Cube them. So it's going to be raised to what power?
3.
To the 3rd. So our first perfect cube is going to be, what's 1 to the 3rd? 1. 1 is still a perfect cube. What about 2 cubed? 8. Yes. 3 cubed? 27. 4 cubed gives us 64. And 5 cubed gives us 125. Again, we're not often going to go above that and expect you to notice it. It's possible, but we're going to use calculators a lot for things higher than that. Okay, so we're going to be looking at all kinds of different types of radicals. We're going to look at cubes, we're going to look at squares, we're going to look at square roots. We may wind up with cube roots. Snap. May end up with all kinds of weird things. So our last one here, trying to get us to remember how to do the mathing part. Boop. The square root of 324. What is the square root of 324? 18. That actually is a perfect square. It is 18. You can type it in the calculator. If that's not one you know off your head, you can always break it apart into pieces and realize that this is definitely going to be divisible by 3, which means it might be divisible by 9. Like, you could divide it up in any number of ways that you wanted to, but this breaks up into 18 times 18. So when we're finding our square root, it's just 18. It is a perfect square. So square roots and perfect squares are undoing each other. If I square something and then I square root it, they undo each other. So what we're going to be working with in this very last section of the semester, which is a fairly short section. So it's going to take us barely more than a week. Our quiz is next Wednesday. Like, that includes reviewing. So like, we're looking like a week. We're going to be looking at all kinds of different roots. Square roots, we'll do cube roots, we'll do fourth roots, we could do eighth roots. We don't really have, there exist names for the higher numbers of roots, but once we get above cube, We don't use them. Practically. We'll say power to the power of 4 instead of saying quartic. Or we'll say the 4th root instead of the quartic root. Like we'll say to the power of 8 instead of to the oct. Or the octic root. Or the nonic root, which would be 9. Yeah. So they exist. The names do exist, but practically real life, nobody uses them. If you're doing anything higher than a cube, use the number. Don't use the Latin root, because Latin. Pshaw. But what we're going to do, you do not need to write the whole paragraph down. Mostly you want the picture. I didn't print it. You want the picture. I thought I blocked most of it out, but this is straight up from your textbook. But you want to draw this picture here. Decent. I thought I added more pages than that.
I'm on the list here.
Yeah.
Let's discuss.
It's. I promise it makes more sense than it looks like. Just making sure that all the things that I have in my version of the notes are in there. Okay. I'm going to even zoom in the page so that we're not looking at near so much of it. There we go. You want this part. We are going to be looking at all kinds of different roots, which means we need to know how to tell what kind of root we're looking at. So the way this is titled is these are called nth roots, where they literally like they're saying third, first, second, fifth. They're saying nth because it's a number we don't know. Inside the same square rooty guy we've always seen, there's just a little baby number inside the little hook. And what that tells us is it's going to tell if it's a square root, or a cube root, or a 4th root, or a 5th root. And the big R underneath, that's our radicand, is what's that called. And that's just the guy underneath. That's who we're looking at. So the default state of our index, if I don't put any number in it, like if I just write it like this, I say, like, oh, say square root of 324, that one we did in the bell work. Our index, nothing's written there. If nothing's written there, there's an invisible 2. If it is anything other than a 2, we will put it there. We're never going to ask you to guess what kind of root it's going to be. So if I was to do something like a cube root, I would put a 3 right there. And I'm just going to grab one of our cubes from the previous page. If we did cube of radicand 27, what number cubed gave me 27? 3. So the cube root of 27 was 3. That simplifies down to be 3. We could do that with any number we want to. I could do a 4th root. I could do a 5th root. I could do a 20th root if I was really feeling feisty. The index tells us what we're looking for. And what that is that's our groups of. So when we're looking at square roots, we're looking for those perfect squares, those pairs of things. If I had a square root of x squared, that would just be x, because I'd have 2 pairs. So in a cube root, we're looking for groups of 3. If we're looking for a 4th root, we're looking for groups of 4. So our index tells us what number of groups we're looking for. But you know, it sounds weird. If there's no index written, it's an invisible 2. We're looking for perfect nths, so perfect squares, perfect cubes, perfect fourths, or you can think of it as groups of 2, 3, or 4, or whatever number's there. And we're going to work with this all day. We're just going to work with these kind of funky roots. But I need more time on a picture. Here's our first 2. All right, so this is what I mean by saying there's nothing in the little hook. If there is nothing written in the hook, what number is it? 2. This is a square root. We're looking for pairs of things. With the numbers, calculators are super awesome at square roots. In this case, we're going to deal with it just like the ones we did last chapter, where I split it up into its different pieces. I'm going to take, just like we would pull that -1 out, I'm going to make this be our square root of 25 and our square root of x to the 4th. When these two pieces are multiplied together, I can split them apart into their own radicals. That makes them easier to deal with. What is the square root of 25? 5. Once I take the square root, don't put it back in the house. The square root of 25 is 5, not the square root of 5. I had a lot of people wind up doing that on the test, where we just square root something 3 or 4 times just because we kept putting it back inside the house. Once it comes out of the house, let it stay outside to play. Okay, the tricky one is when we start tossing letters in there. So I want to know the square root of x to the 4th. You can either do it with the process of what squared gives me x to the 4th, or the way I like to think about it is I have socks. They're strange looking socks. They look like x. And in this case, I have 4 socks. They're very strange looking socks, but it's 4 socks. I want pairs. How many pairs can I make out of 4 socks? 2. So I'm going to have 2 x's. They're strange looking socks, but we're looking for pairs. That's what square roots are looking for. So square root of 25 x to the 4th is 5x squared. That's our answer. If you want to push them closer together, that's fine, but I'm totally fine with the space in between two. Just don't put a plus. All right, when we have things that have these kinds of quantities in there, think of this as a really weird looking sock. Don't multiply it out. X plus 7, quantity squared. That means I have a funky looking sock and I have 2 of them. How many pairs of funky weird socks can I make? Just 1 pair. The square root and the square cancel each other out. They undo each other. There's a name for that, but we'll talk about that next semester. So the square root and the square cancel out. So this thing's just going to simplify down to be that, not a pen, x plus 7. The square root and the square cancel out. We can think of it that way. We can think of how many funky looking socks I can make. Or pairs of socks. I promise there's a reason for pairs of socks thing. I know it's weird, but I promise I'll make something simple. I have reasons. Looking for pairs in these ones. In square roots, we look for pairs. We're going to try a couple more funky ones before we start tossing weird indexes at you. Okay? Promise I'm going to work you guys in slowly. Get back up to it.
Ew.
Funky looking socks. If we have a quantity, treat it as a funky looking sock. So here, I'll give us some of my beautiful art skills. So here we go. I'm so good at drawing things. It's a sock. It's a weird sock, but it's a sock. I'm so good at art, you guys. Oh my gosh. Totally my skill set. It's a sock. Ish. All right, so when we have a quantity, treat it like a sock. It's a weird looking sock, but it's a sock. So I have y cubed minus 3 as a group to the 8th power. That tells me I have 8 really weird looking socks. How many pairs can I make out of that? 4. So I'm going to have my funky looking sock, my y cubed minus 3, and from my 8 individual socks, I'm going to make pairs because there's no number here. I have 4 pairs that we get. what if it had been a 9? What if I asked you for the square root, I'm going to have the exact same piece, our y cubed minus 3 to the 9th? I was going to say, how many pairs can we make? If I have 9 socks.
4.
I can still make 4 pairs, but I have
1 lost.
1 left over. 1 lost, lonely, friendless sock. He stays in the house. So my pairs of socks, they get to go in the drawer. These guys come outside, they get to go in the drawer, they get to hang out, they get to play, they get to do whatever they need. So if we have leftover bits, they just get stuck inside. They're left in the missing sock basket. So this one, if we have to the 9th, we would still wind up with our y cubed minus 3 to the 4th, but we would have a leftover y cubed, minus 3 inside. So we are still looking for pairs, looking for pairs of socks. And technically you can do the decimal thing, but we're not. We're going to get into that more tomorrow. So I was going to say, because I heard your instinct on that one. What's up?
So, since it's even, right, we can make 4 pairs with 8 socks. We wouldn't use the square root anymore, they will cancel out.
They're canceling out. That's what it's doing. Yeah. It is still doing the square root. It's finding our pairs in there. It's just kind of a different way of thinking through it. It's still finding those pairs. It's still finding the perfect squares inside there. All right. So now let's look at this one on the right that has a gabillion different things. I've got my square root of 12, x to the 7th, y to the 9th. So the first thing I'm going to do, because it makes things easier, is I'm going to split it up so my 12's in one radical, my x is in one radical, and my y is in a different radical. So I'm going to make this be the square root of 12 times the square root of x to the 7th times the square root of y to the 9th. We can do that. We did that last chapter with the square roots. We did that in the first page with our 25x to the 4th. We did that there. So let's see if we can simplify some of these things. Let's look at our square root of 12. It's not as easy to do that one if we think about it as socks. Not impossible, but it's tricky. How are we going to do square root of 12? I can rewrite 12 as 4 times 3. Why do we like 4 times 3 more than 6 times 2? Because 4 is a perfect square. Exactly right. Exactly right. So that list of perfect squares that we had, that's what we're trying to aim for in here. I want one of these in here to be a perfect square if possible. So this lets me write this as that square root of 4, which is 2. Now he gets to be outside the house, but that lonely 3 is stuck inside. He doesn't have a buddy. He is a mismatched sock. What about for x to the 7th? What are we going to get for the square root of x to the 7th? We can make 3 pairs and we have 1 left over. Yes.
3x, 1
So don't put the 3 in the front. It's a power. So it's going to be our x cubed, and we had our leftover x. You can absolutely 100% do it like that. If you want to write it the same way we did over here, where we make it be something like squareable, you could write it as x to the 6th times x, if that helps you see it. If that does not help you see it, you don't have to do that step. I'm just splitting these up into pieces that are easier to work with. What about for our y to the 9th? Yep, y to the 4th square root of y. Because we could split up our y to the 9th to be y to the 8th times y, because that gives me something that's square rootable. Square root of y to the 8th is y to the 4th, and we have a leftover y. But this is a messy, 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 messy looking statement down here. All the things that are outside the radical go together. All the things that are under the radical go together. So we're going to rearrange it so that I don't have 3 separate radicals. We're going to get back to 1. So everything that's outside, I'm going to have my 2x cubed y to the 4th. I still have my square root here. All of my lonely bits go inside. My 3, my x, and my y. Okay. Questions on that bit? Because we talked about funky indexes, but we've only seen square roots so far. I wonder what can be next. The questions on this before I start tossing indexes at you. Okay. Here's your first official cube roots. When we do square roots, we looked at socks. You know why? Because we have 1, 2 feet, for the most part. Some people only need 1. But with cube roots, it's not that we're looking for socks for people. It could be like a dog, getting him socks. They're so happy.
That actually is kind of sad, though, to think about.
Like, there's not another 3-legged animal I can use. When it's 4th roots, I do use a cat. Tricycles don't need socks.
Stools have those gripper grabber things.
Yeah, okay, if you got a 3-legged stool at Grandma's house that has the little stool socks. Mother-in-law has those, but that's the only difference. So it's the same kind of vibe. Think of them as weird socks. We're looking for groups of 3. The index is your groups of. It's how many feet the particular creature has. Maybe we just have a weird dragon. What's up?
You should just do a heart. You got 3 bars.
They have like 3 toes on each foot. Yeah. Could do a single foot of a 3-toed sloth. Turtles have 4 legs.
No, I'm saying they got like 3 toes.
No, they don't.
Okay. I was like, some do. Elephants have 3 toes, but I don't put a sock on each individual toe. That would feel weird. Toe socks used to be a thing though. Like, but they were all attached to one sock.
Toe socks are
I used to have T-toes.
I was gonna say, it's been a hot minute, but
They really better than back.
okay.
They got like.
I know. So we're looking for groups of 3. When we have something that's a perfect cube like this, or when we've got an 8, sometimes with the numbers it's harder to spot. We do try and usually give you something that is visually there. But if it's not something that we instinctively notice, what you can do is you can fully factor this. So I could write 8 as 2 times 4. That's something we know. I could split the 4 up to be the cube root of 2 times 4. I could write as 2 times 2. How many 3s do I have under my square root now, or under my cube root now? I have, how many 2s are under here? 3 of them. And we're looking for groups of 3. Okay, so we're looking for groups of 3. Think of it as, again, weird looking socks. They just look like 2s. I'm looking for a group of 3. I only have 1 set. So this is going to come out of my radical, and it's just a value of 2, because 2 cubed gives us 8. Cube root of 8 gives us 2. So you can still do the numbers in the same kind of way if the perfect cubes is not something that sticks in your brain particularly well. You can absolutely do it by factoring things down. We're then just looking for groups of whatever our index is. Groups of 3. If our index was 4, we look for groups of 4. That kind of vibe. On our middle one here, we've got the cube root of 125, x cubed, y to the 6th. So again, just like I did with the square roots, I'm going to break these up to be separate pieces because I don't like them all smushed together. It makes things complicated. So I'm going to have my cube root of 125 and my cube root of x cubed and my cube root of y to the 6th. And then we're just going to look at these individually. What is the cube root of 125? 5 cubed gives me 125. Or you can come through and factor it. 5 times 25 gives me 125, which means you'd have 5 times 5 times 5. Here's my group of 3. Our next little segment, I've got my x cubed. So I have 3 x-shaped socks. How many groups can I make? Just one. I need groups of 3. Do I have any left over? Nope. So this just becomes an x. One set. How about on my y's?
2.
We have 2. I have 6 Y-shaped socks. I'm looking for groups of 3, so I can make 2 sets. These pieces are being multiplied together. I'm going to rewrite it just because they're really far apart. So our final answer here is 5x y squared. And the next one is super icky looking, but do it the exact same way we just did the last one. We're going to take our root and we're going to smush things together. So I'm going to rewrite this as the cube root of 64, the cube root of x to the 5th, over the cube root of 27, and the cube root of y to the 7th. It's gross, but if you split it up like this, taking each separate term, my numbers separate from my x's, separate from my y's, it makes it easier because you just zoom in. Because I just want to look at first things first, this cube root of 64. We have ways to simplify things on the calculator. I wonder if there's a way to do a cube root on a calculator. Because if that's not something we remember, because we don't work with perfect cubes all that much, there is a way to check it on the calculator. So, boop. It's actually a different button. When we do square roots, it's on the square. So it's this little green one up here. So what we do first on the calculator is you put in your index. So we're doing a cube root, so I'm going to put in my index of 3, my cube. Then, just like when we go to square roots, we have to hit the green button. And it's actually this up arrow right here. That's the raise it to any power button. So when we hit the second, it does our take it to any root button. These calculators are not as good with simplifying. It will tend to give you decimals if something doesn't come out perfectly. So if you get decimally answers, that means go look through and find your socks to simplify. But the cube root of 64 is in fact 4. So if we're not 100% confident on our first 3, 4, 5 cube roots, there is a way to get them on the calculator. So the cube root of 64 is just 4. Whoop, not a pen. Got it. What about with this cube root of x to the 5th? What are we going to get there? Yes. So I could take my cube root and I could make this be x cubed times x squared. That does the same thing. That still would give me x to the 5th. Or you can think about how we have 5 socks. If I'm looking for groups of 3, I can make one proper set. And we have a leftover 2 socks. They were in the numerator originally, so they are still in the numerator. Same vibe with the denominator. If it was down here, it's going to stay down here. So what is our cube root of 27?
3.
Mm-hmm. This guy's just a 3. How about our cube root of y to the 7th?
There's 2 groups of 3.
There's 2 groups of 3, so how are we going to write that? Y to the what? Swap
Y
it.
squared.
Y to the 2. Y squared. How many leftovers do we have?
1.
We have just 1. So it gets its own little cube root house that it's stuck inside because it has no friends.
Oh, how sad.
Radical land's a very good place. Okay. So questions on some cube roots? Because I could start tossing all kinds of wild numbers at you. I could give you 4ths is the last ones. So if square roots, we look for pairs of socks for people. Cube roots, we look for pairs of socks for our very sad but very happy 3-legged dog. Groups of 4, it's a cat. Or a non-3-legged dog, a regular dog. Groups of 4. You can use your calculator for these things, especially for the numbers. You could do our 4th root, or we can try and think of what number to the 4th power gives us 16. 625. Or we could take this and make this be our 4th root of 16 and our 4th root of x to the 4th over our 4th root of 625. And realize that 16 is a whole lot of even numbers. I could rewrite this as our 4th, yep, it is. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. So 16 is the same thing as 2 times 2 times 2 times 2. And we're looking to make sets of 4. How many sets of 4 do I have in those 2s?
1.
I have a whole set. Do I have any extras?
Nope.
Nope. So the 4th root of 16 is just 2. How about the 4th root of x to the 4th? What does it say? It's x. That's 4 socks. Making a set of socks for my cat. She needs 4 socks. She's got 4 legs. So we have 1 set of socks. How about for this ugly one in the denominator, the 4th root of 625? Ew.
5.
It's 5. This is the same thing as 5 times 5 times 5 times 5. So looking for a set of 4, we have 1 whole set. Okay.
I thought it was smaller.
What's up?
I thought we were counting how many.
Yep. 625 is 5 times 5 times 5 times 5.
I got that.
Uh-huh.
I just put that in my calculator.
This one?
I just put it in the calculator to make it sound.
I was like, you can do it in the calculator. You absolutely can. You can do 4th root of 625 and it should spit out a 5. The only problem is if it wasn't a perfect square. So what if I had 4th root of 32? 16? Yeah.
The 4 is 16.
Mm-hmm.
I just had to put 4.
Because you're going to break it down
Yeah, you have to break it down to the
You have to break it down as small as you can. Yeah, we're looking for sets of 4. So we got to keep going until I find 4 of them, or I can't go any smaller. We'll do more with more remainders as we go through this, like the leftover bits. Right now, a lot of them are coming out fairly tidy. All right. Last one. 4th root of 81. What is going to be the 4th root of 81? I could split 81 up to be, yep. This one is 9 times 9 is usually the way we spot it. Well, I don't have a set of 4 there, but each 9 could be 3 times 3 times 3 times 3. That gives me a set of 4. Hello, thank you. So the 4th root of 4 3s gives me one single set. How about our 4th root of x to the 7th? What are we going to get here? Mm-hmm. And how many leftovers are we going to have? 3. How about for my y's? Y to the 3rd. Do we have any leftovers? Nope, because I can make 3 entire groups of 4. So when I write this in my final answer, I'm going to have my 3, then I'm going to have my x that's outside the radical, then I'm going to have my y cubed, and the radical goes last, my 4th root of x cubed. Okay? We are going to keep working with these. We'll work with all kinds of weird fractions and indexes and all kinds of funky stuff throughout the rest of this chapter, but we're focusing a lot on these kind of funky roots. Okay? So, I'll pull up announcements. I'm going to pass out homework 1. I think we only have 3.
Wait, this one's that last. 4, 1.